All right, good morning. Let's get started while the others arrive. So, last week we discussed about the large signal amplifier analysis of the BJT amplifier. Mainly we looked at biasing, different types of biasing, and why we need to bias. In amplifiers, we said if you want to make sure you get the whole signal, not part of it, amplified, if you want to get the signal shape preserved, one thing you need to do is to shift the origin. In other words, apply a signal even when there is no signal, a DC signal, so that it's operating in the linear region. Linear region in BJTs is the active linear region, but a similar thing can be applied for the MOSFETs as well, where we again do the biasing in order to keep the operation within the saturation region. Saturation is the linearized region, or the this is the region where the MOSFET operates as an amplifier, right? So for that we need to first shift the origin, so the DC signal is applied, and then later on we will see that we need to make sure the signal, if you want to fully linearize the signal, we have to make the signal small also. That will come eventually in the small signal analysis. Right, and also we looked at the thermal runaway, and we inserted a resistor in the emitter circuit. These resistor value in the emitter circuit, even in the amplifier, to avoid thermal runaway and to improve the AC gain. We said when you insert the emitter resistance, the total gain of the system goes down. But if you want to increase the gain in the for the AC signals, which is basically the requirement most of the time, we are not much interested about the amplification of the DC, but the AC, right? So therefore, we bypass the emitter resistor using a capacitor, which acts like a short circuit for the frequencies of interest that we are working on. And sometimes we also have a particular resistance even for the AC path, for the AC frequencies, just to make sure that we have the control over the gain, rather than having the emitter spread resistance decide what the gain is, right? So therefore, we looked at those things, and we also looked at the load line, DC load line and the AC load line, and we then did a example on this large signal analysis, so the biasing and load line section. And also we said that by making sensible assumptions, we can actually make our lives much easier, right? Especially simplifications can be made a lot easier if you make sensible assumptions. Any questions up to now, this section? Up to this section, any questions you have? All right, so then we are going to move on to a different section, which is called amplifiers, or classification of amplifiers, which is more of a more general section first, and then we will be applying these principles later on in our small signal analysis. Okay, so let's get started with that. Classification of amplifiers. Now, if you take an amplifier, the purpose is to increase the signal, right? Now, when we call signal, so in electricity, the signal can be either a voltage or a current. Can be a voltage signal or a current signal, right? So sometimes we want the exact value of the current, but we really don't care what the voltage is. The voltage can be anything, but we are really interested about the current. We need to make sure that the current is constant. For example, current sources. We don't really care what the voltage is applied is, as long as the current outputted by the source is a constant value, or whatever the shape of the current is. Whereas there are some other circuits, what we care about is only the voltage, and we don't really care what the current is. Current can change as required to maintain that voltage, right. So the signal in an amplifier can be a current or a voltage. In fact, when you look at a black box as an amplifier, okay, so if this is an amplifier, so there are two ports. One is the input port, the other is the output port. This is the amplifier. So input can be a voltage or a current, right. Or an output is also, it's possible to have a voltage output or a current output. Right. So as I said, input, sometimes what I am interested about is V in. Sometimes I give at the output of a signal generator, which is voltage output. The voltage is the controlled variable. Sometimes the input is a signal coming from a microphone. Maybe it's a current, or maybe the LDR, output of a LDR, in which case the input is actually a current, not a voltage. Similarly, so the input can be either a voltage or a current. Likewise, the output also can be a current or a voltage. Okay. So so there are two possibilities for the input, two possibilities for the output, which makes it, I can input a voltage and get an output voltage, or I can input a voltage, but the output of that amplifier may be a current. So it, in addition to amplifying or increasing the power, which is an essential requirement, increasing the power is the most important thing about an amplifier. Amplifier has to always increase the power, whether it is current amplifier, voltage amplifier, whatever the other amplifier, it has to amplify the power. So V times I input has to be less than V out times I out, right, so the power. So I can input a voltage, but output can be a current. So in that case, in addition to increasing the power, it has changed the variable from a voltage to a current. Likewise, input can be a current, output can be a current or a voltage. So there are four possibilities for these amplifiers, depending on what its task is, whether to convert a voltage to a voltage, voltage to a current, current to a voltage, or a current to a current. We have four different types of amplifiers. So the first one is the simplest one. They are all simple. The first one we can think of is a voltage amplifier. So in a voltage amplifier, my input is a voltage, output is also a voltage. So if I draw the black box model, this can be implemented using op amps, BJTs, FETs, or a combination of all of these, we don't care. What's inside, we really don't care what it is. It's as long as it's a linear amplifier, and whatever it is that is inside it, we know that it amplifies the signal. In this case, it amplifies or increases the voltage by a certain constant value, right? So such an amplifier, so we have this input and output ports. So since this is an input voltage, whatever that thing that is before this input, we can represent as a Thevenin's equivalent circuit. It can be a microphone, it can be a signal generator, it can be some other stage of an amplifier. We don't mind. Anything, it can be anything, but we can represent that as a Thevenin's equivalent source, right? So what we represent it as is a Thevenin's equivalent circuit, something like this. So my source voltage is Vs and source resistance is Rs. And the voltage input to this circuit is V in. And I don't really care about the current, right? It can be anything that you want. And when you connect it outside, I can load it using a resistor. So this is the load. So let it be RL. So I am connecting. This RL may represent an actual resistor, a load, or in fact the input impedance of a second stage or another stage, right? So this again can be anything, but we are going to basically represent the next stage as a load whose input impedance or resistance is RL. Okay? So here again my interested variable is V out. That's my output variable. Now, for a voltage amplifier, what I want is a constant relationship between output over input, right, voltages. So what I would like to have is something like V out is equal to AV times V in. That's what we like to have, right? So AV is defined as V out over V in. This is the definition of, so when I put a triangle, that means it's a definition, right? So, so let's find what this is. Now, as I said, this is an output voltage. So therefore, whatever that is inside this black box, I need to represent it as an output voltage source. That means I need to represent it as a Thevenin's equivalent circuit, right? That's what gives me an output. So therefore, what is inside this is a voltage source in series with a output impedance, right? So this voltage is let's call this R out, and this one has to be the voltage gain that I want, that is AV times that voltage V in. So that's my Thevenin's output voltage, which is basically related by this definition. And of course, the input, when I connect this to the Thevenin's equivalent circuit, in general, this amplifier may have an input impedance. So therefore, what we mark this as a resistor. Okay? So this is R in. So if you look at this particular circuit, this whole black box, which may have hundreds or thousands of transistors, BJTs, MOSFETs, op-amps, whatever it is defined by 1, 2, and 3 variables. R in, R out, and AV. That's all you need to know about this black box. Once you know these three variables about this black box, the whole thing is defined. Okay? Now, so what's actually happening here when you connect it like this, let's see whether this output voltage is actually equal to the V in times AV. Now, the first thing is, as soon as you connect it like this, V out, there's going to be a current. We don't care what the current is, but as soon as I connect it, there is going to be this load is going to draw a current, right? This current, let's call IL, right? The load is going to draw current IL. Because of this current, that is the same current that passes through this one as well as that, the same current. Because of that, this output voltage is no longer the same voltage that was there before I connected this load. That voltage was the open circuit voltage, which was equal to AV times V in, AV times V in. But now I have connected a load which draws a current. Because there's a current, there's a voltage drop across this output resistance. Because there's an output resistance, the output available at the output is now less than the previous one. And as soon as you look at this, this is a recurrent circuit that we have seen before. It's a voltage divider circuit. This AV times V in is divided between these two resistors in their resistor ratio. So, actually V out, when connected to this circuit, becomes AV times V in times RL over RL plus R out. So, this quantity is always less than or equal to 1. It can never be greater than 1. So, there's a if this R out is 0 in ideal case, then the whole voltage appears at the output, otherwise there is some drop. So, for voltage amplifier, we prefer this R out to be 0, so that as much as possible you get that amplification out. In practical circuits, there is a value for this. The larger the value, the worse the circuit, right? Because you are going to drop that voltage across this R out. So, we like it. We like the R out to be as small as possible, right? So, that is the first thing that we need to know. Now, our source is what I want to actually to amplify. If this can be my microphone. What I want is the microphone signal to be amplified by a certain amount. But what happens here? This is V in. Now, as soon as you connect it to this black box, the amplifier, this has an input impedance. Again, just like that, you have a voltage source in series with two series resistors. Again, you can see this V in, this term V in can be written as V in is the voltage across this, is equal to Vs times R in over R in R plus Rs, right? Is it clear? So, that voltage drop, because when you connect it here, there is a current road, and then because of that current, let us call this I in. Because of this I in times Rs is dropped. So, that is not available for me. So, what is available is what is there. So, this can be rewritten by replacing V in here, AV times RL over RL plus R out times R in over R in plus Rs times Vs. So, actually what I would have liked was this Vs to be multiplied by AV. But when I connect these together, what happens? that value comes down by two factors. One, due to this loading effect of the resistor. Two, due to the loading effect of the input impedance. Now, if I want an ideal voltage source, would I like this Rin to be very small or very large? I want as much, so I want this to be very close to 1 and this to be very close to 1. We have already looked at how to make this close to 1. If R out is 0 or very small compared to RL, then almost all the voltage that's there will appear out there. But there is another voltage drop across this. So, you can't change RS. RS is something that is characteristic to the source. You don't have any control over that. It can be a microphone with maybe 50 kilo ohms or 10 kilo ohms output impedance, maybe a signal generator with 50 ohms output, that you don't know, right. It can be a very high output impedance source, like if you are getting an ECG, it can be like 10 kilo ohms output impedance, you don't know. So, therefore, you don't have any access there. So, what would you like if you want as much of Vs appearing as V in? What do you like for R in? Should it be a small value or a large value? It's a large value, right? Should be as much as possible, ideally infinity. So, ideally infinity. So, this should be R in should be close to, we like it to be infinity, R out 0 and AV whatever we like, the desired value. Okay. So, if ideally R out is 0, R in is infinity, and if R in is much bigger than Rs and RL is much bigger than R out, then this is almost 1, this is almost 1, AV is approximately equal to V out over Vs. So, this is roughly equal to this, these two are almost 1 to that. That is what we would like, right. So, ideally this is the relationship that we would like to see. So, we are using a Thevenin's equivalent circuit for this. For the output, right. Clear? Very simple, but you need to understand why we need each of these particular values. Right. Now, the second one, all right, we have a voltage amplifier. The second one is you can input a current and take an output of current. Okay. So, if that is the case, the second one is a current amplifier. Current amplifier. Okay. So, if you draw the black box there, you have an input and output port, and I connect it to a load resistor RL. Now, my input is a current. So, if my input is a current, it makes sense to model whatever is before this circuit as a Norton's equivalent circuit rather than a Thevenin's equivalent circuit, because what I control is the current, right. So, therefore, I represent this as a the Norton's equivalent circuit, where this is my Is and this is Rs. This is a source resistance and a current value. Obviously, if you wish to, you can convert this from this form to Thevenin's equivalent. You can easily change between these two models without much difficulty. but this is what you have now. Now, in this case what we are interested about is this I in, and output we are interested in output voltage there. So, that is equal to I out. Okay. That is what I am interested about. Voltages I really do not mind what the value is. So, the first thing that we need to again say is, as soon as I connect here, it might load the circuit because of this input impedance of my thing, right. So, therefore, I am going to draw some current based on that. The second of all, the output has to be a current. So, therefore, again I am going to use a Thevenin's equivalent circuit rather than the Norton's equivalent circuit. Now, this is a controlled current source, this is a dependent current source. So, therefore, I am going to use, it does not matter, you can use some notation like this, but I have been using this notation for dependent current source. So, therefore, I am using it here. In my lecture note, I have the previous notation, it does not matter, you can have it, but to be consistent with my notation earlier, I am going to replace this here. This value is AI, that is the constant that defines the current that is coming in and current going out, times I in, right. So, that is the relationship. But at the same time, you also have a Norton's equivalent resistance, which we call R out. Okay, so, those are the, so the three things again we have R in, R out, instead of AV now we have AI. These are the three things that characterize fully this current amplifier. So, we are using Norton's equivalent circuit here, right. So, just like this, I out is defined, sorry, I out. So, let us start with the definition. So, AI is defined as I out divided by I in. Okay. So, I out divided by I in is equal to AI. That is the definition, right. So, but when you connect it here, what happens? Depending on the values of these two resistors, part of the current flows through this, not all of this AI times I in flows through this output load, some of it actually goes through that. Likewise, some of the current that comes here IS, part of it go to the circuit, but part of it flows through this internal resistor, output impedance, right. So, therefore, I can write AI as first I out is equal to AI times I in, that is this current coming here, and they divide between these two in just like voltage ratio, this is a current ratio, right. So, therefore, the bigger one gets the lower current, larger resistor gets a smaller current, right. So, in this case the ratio becomes R out over R out plus R L. Now, earlier what was, this is the same quantity, but this was R L for the voltage division. So, that the bigger voltage is across the bigger resistor, but here it is the other way around. Okay. So, that is my current there. We looked at that also in the recurrent circuits section, right. We looked at it. So, we know we can directly write this. So, that is less than, sorry, this is V out. V out is equal to AI, so I out is equal to AI times I in times that. And again, likewise, we can represent I in as Rs over Rs plus R in times Is, right. Similar argument, Is comes and divides into 2. The larger resistor gets the smaller portion, the bigger one gets the larger one. So, therefore, you need to interchange these values. So, therefore, you can also write this as AI Is times Rs over Rs plus R in times R out over R out plus R L. So, that is the output relationship. So, that is the output current. Now, as you can see, for practical circuits, this will be less than 1, this will be less than 1. So, therefore, I will not get the full current gain that I can. If I want to get as much of it as possible, what I need to do is to make sure that this load is much smaller compared to this output impedance, so that most of the current flows through that load, not through the output impedance. So, the bigger the output impedance, smaller the current that goes through it, which is better. So, in the ideal case, this output impedance has to be infinity, right. So, R in out has to be infinity. Similarly, because we do not have any control over Rs, there will be some component going through this Rs, and if you want to minimize it, if you want to minimize that component, we need to ensure that this R in is as small as possible compared to Rs. Ideally 0, right. So, this has to be 0, this has to be 0, this has to be infinity, ideally. So, ideally R out is infinity, R in is 0. Now, this is totally different from here, R out 0, R in infinity. So, this is totally different for the voltage amplifier. Practically, if R out is much bigger than RL and R in is much less than Rs, then we can say I out is roughly equal to AI times Is. That is what we want, right. We want the current source to be amplified. In order to do that, we need to ensure these two conditions. If that is the case, this AI is independent of this and that. See, AI will be, so AI, if this term is much smaller than this, then this will be, we can make this equal to 1. And if this term is, sorry, this Rs has to be much bigger than Rin, Rs has to be much bigger than Rin, so this is 0, so this is 1, and R out is much bigger than RL, so therefore this is infinity, so that again is 1. If that is the case, AI will be equal to I out over Is, meaning that whatever the value of Rs, it can be 10 kilo ohms, RL can be 1 kilo ohm, doesn't matter, output gain will be the same, current gain will be the same. But in order to do that, we have to have that condition, right. Practically they are not, but we have to make them as close to, as large as possible and small as possible. Typically when we say small, for resistors, the practical values less. Now typically the resistors that we use are in the range of kilo ohms, like typically 500 ohms upwards, like 1K, 2K, 10K, 50K, up to about 100K. Anything above that for this course are large. So typically 500K resistor is a large resistor. 1 mega ohms resistor is a large resistor. Okay? 20 ohms resistor is a very small resistor. So what we try to achieve is this beyond this 100 ohms to 500K kind of a range. So practically what we achieve is input impedances of maybe about instead of 0, 100 ohms. Output impedance of maybe 1 mega ohm instead of 0. So those are good values. Those are practical values, not ideal, right? Clear? Right. So now likewise, now we have looked at 2 cases. There are 2 more cases. Very simple. All we need to do is repeat this, right? For different things, what will vary? If my input is a current, I will have a Norton's equivalent circuit. If my output is a current, I will have a Norton's equivalent circuit. If my input is a voltage, I will have a Thevenin's equivalent. Output is a current, output is a voltage, I will have a Thevenin's equivalent circuit. That's all, right? And then for Norton's equivalent circuits, I like whatever comes as parallel in resistance to be very small, so that most of the current goes through that, whether it is in the input or output. In other words, Thevenin's resistance, the source resistance has to be much bigger than whatever is connected as the load. Okay? And Thevenin's on the other hand, we like the output resistance or the Thevenin's resistance to be as small as possible compared to the load, whatever is connected. That's all that there is, right? So the third one we'll take, we have a, now so far, what are the units of these gains? AV and AI? Units are volts divided by volts, no units. It's a scalar. That's a scalar, right? Scalar. Similarly, this one, AI, I divided by I, amperes divided by I. This is a scalar. These are scalar values. You just scale it. But what happens if I have an input as a voltage, so that you have a Thevenin's equivalent circuit here, and load is RL. What I want to take out is not a voltage, but a current, right? So my input is a voltage, but my output is a current. If this is the case, then obviously the first stage is simple. You mark it as a resistor R in, but the output, since I need a current, I mark it as a Norton's equivalent circuit. So for that, what do we use? I have to multiply a voltage by this gain. So VI, V in times some quantity. Now this quantity, if it's a scalar, we input a voltage and get a current. That's not going to work. So therefore, this gain is going to have the units of V equals IR. So I is equal to V times 1 over R, right? So that is the conductance GM. So this we call GM, because it has the units of conductance, 1 over resistance, 1 over ohms, right, or Siemens. So therefore, this is called transconductance gain. So trans is between. So what we are going to is convert a voltage into a current. So you are going to multiply by a conductance, right? So these are called transconductance amplifiers. So, their GM is defined as output current divided by input voltage. So, the units are 1 over ohms, or sometimes you call mhos or Siemens, right. So, 1 over ohms is the 1 over ohms is the unit of this thing. Okay. So, now I can do the same thing. I out is equal to GM V in times GM times. So, I out is GM times V in, but when there is a current flowing, this is going to load, this is going to divide the current between this and that, right. So, there is some current going through this, and there is going to be some voltage here, right. So, because of that, this is going to be, I am going to write it directly, because of this I will have a voltage drop R out over R out plus, this is the current ratio, RL, this is the load side loss, and then in the source side I will have R in this loss. Okay. Ideally, I want the whole voltage applied here, meaning that R in has to be infinity, R out has to be what? Infinity or 0. I want the whole current passing through this RL. Should this be 0? Infinity. Should also be infinity. So, this is also infinity. Okay. They both have to be very large for transconductance amplifiers. So, if R in is much bigger than Rs and RL is much smaller than R out, then GM is roughly equal to I out over IS. Under this condition, then so GM is independent of RS and RL. These are external things that we don't have. Yes. Sorry. Thank you. Right. You got 1 point. Right. There was a sorry. I out V in. Sorry. Say that again.
In the second equation, I out should be GM times Vs instead of Vs.
Yes. I out this now. I out is equal to GM times
Vs.
huh?
Vs.
This one? No, this yes, that is correct again. Yes, because I have taken that also there. Right. I think you are Shankar, right? Ishankar, right? The one behind, yeah? Yeah, I think you were also trying to point it out, so I am going to give 1 point each for both, right? Because I appreciate that you try to say that, okay? 1 point each. The same thing that you were trying to say, right? Right. So I am going to give 1 point each for both, right? Okay. Right. So this will be like that. So the other circuits also the same, right? When you have these conditions met, then they don't depend on this RS and RL, which we don't have a control over. They are external things. So therefore, we as engineers, we design these circuits to be very close to these ideal conditions as possible, so that we don't have to worry about what we connect there. Okay, that's the purpose, right? So likewise, now we have the last one. Now there what do we have? Input is a current, output is a voltage. So therefore output V is equal to I times the gain. So that should be an R. So therefore the gain is a resistance. It should have the units of a resistor. In other words, ohms. So we call these kind of amplifiers trans resistance amplifiers, right? Trans resistance amplifier. That's the fourth type of amplifier. So I don't have to spend too much time on this. By now we are all familiar with this. The input is a current, output is a voltage. And since input is a current, I am going to use the Norton's equivalent circuit for my input. And since the voltage is an output, I am going to use a Thevenin's equivalent circuit for my output circuit. Like that. I can quickly write these terms. This is IS, this is RS, this is R in, this is R out, this one is RM times I in, where this is my I in and this is my I out, V out, this is RL. Right. So the rest of it you should actually be able to quickly write. RM is defined as V out divided by I in, and I can then write V out is equal to IS times RS over RS plus R in times, this is the input side loss, output side I have RL plus R out times A times RM. That's my total gain. So ideally R in has to be 0, R out has to be 0. Right. If R in is much less than RS and R out is much less than RL, then RM is roughly equal to V out over Vs and independent of RL and RS. Yes. Sorry? V out over IS. Yes, thank you. See, that's good that I make mistakes, isn't it? Right? V out over. So there are 3 points already today. I'm very happy. I'm not happy because I'm making mistakes, but I'm happy. But you are engaging with the class. Okay? So that's the objective of bonus points. Right? Good. All right. So that's basically what we have. Now with that, these 4 we can see. If necessary, we can actually summarize what are desirable properties of each of these amplifiers. Let me quickly do that. ideal characteristics. Okay. So you have the parameter, you have R in, R out, transfer gain, transfer characteristics. And there are 4 categories. One is the voltage amplifier, current amplifier, transconductance, and transresistance. R in, this has to be, input has to be very large so that it doesn't draw any current, infinity. Current output, output impedance has to be very small so that no voltage drop across this. And transfer gain, AV is equal to V out over V output I DI. Current amplifier, the opposite of this, very small input impedance so that almost all the current flows through this. Output impedance very large, so nothing goes through that, only flows through the output impedance. Current gain AI is equal to I out over I in. Here you have both infinity, so that input is a voltage, so everything is across its input, and output is a current, so no current goes through its internal resistance, and GM is I out V in, and here is the other way around. Right. Okay. So that's basically the summary of amplifiers. We are going to use this in the future when we are characterizing, we are analyzing small signal analysis. We will represent, or we will model the amplifiers using that. Especially, we are going to use this in feedback amplifiers and multi-stage amplifiers. When we use multi-stage amplifiers, we are going to use this to calculate the actual gain when you cascade multiple stages one after the other, right? So we'll get there, but for the time being, we'll leave it there. Any questions up to this? So the take home message is, if you have a linear amplifier, you don't need too many variables to characterize it. If you can define these 3 things, R in, R out, and the transfer gain, then you pretty much know everything about this circuit. Okay? So that's basically the idea. So we will be using this to simplify our analysis. So we, rather than worrying about large, circuits, we simplify them by replacing them with Thevenin's or Norton's equivalent circuits. The next stages we are going to represent using their input impedances. So and then as a load we connect it with questions. Any questions? Any questions? No? Okay. Yeah? Please, if you don't understand, please let me know. Okay? We can clarify. Right. All right. So now with that behind us, let's now move on to some practical amplifier configurations. We'll talk about BJT amplifier configurations and MOSFET configurations. They are very similar. Actually, if you look at one family of, let's say BJTs, the other configurations are very similar with similar characteristics also, right? But let's first look at the amplifier configurations. That's BJTs. So since there are 3 inputs or 3 terminals for a BJT or a MOSFET for that matter, right? So these are 3 terminal devices. You have an amplifier with 3 terminals, right? In the case of BJT, what you have inside is right, so something like this. So base, collector, emitter. In case of the FET, you will have gate, drain, and source. Very similar, right? No matter what, you have 3 terminals, which means if you use what you want is amplifiers. So there should be an input port and output port. So you can pick one of these ports as the output, the other as the input. Then whatever is remaining becomes the common one. You have to input the signal with respect to the other one, right? So rather than saying it in this way, we'll say you can pick any one of the 3 as the common input. So common terminal with respect to what? We give the input and take the output. Okay? So that is how there are 3 different configurations. Actually, you can if you when you pick this, you can pick input output also in different ways. You pick, okay, I pick emitter as the common terminal. Then input can be gate or the collector. Output can be the other one, right? So in which case we should have total 6 configurations, isn't it? There should be how many? 6 configurations. But we only have 3. Why is that? Why should you have only 3 configurations when there are all 6 possible combinations? Have you ever seen an amplifier with emitter is the common circuit, common terminal, collector is the input and the base is the output? I haven't. Why is that? Why is that? Anyone? For 1 point? Anyone? Yes? Collector, emitter current depends on the
No,
collector current depends on the base current. Is that why it is so? Okay, that is one answer. His answer is because emitter current, collector current depends on the base current. You have to have the emitter as the output and the base as the input, right? Dependence of emitter, right? That another. You raise your hands. Yes. Sorry. Gain is less than 1. That's actually the reason. This actually is in a way related to that, because if you look at the gain, the relationship, and the output current IC is AV times beta, and beta times IB, and AV is large. So if you reverse it, what will happen is the gain will be smaller, then it will not be an amplifier, right? So that's the main reason. So you have to pick the right terminal to make it as an amplifier, right? So we are looking at amplifiers. No, that's the reason. Yeah, thank you. I will give both of you points. So you earn 2 points, you earn 1 point, and there are like altogether 4 people earning bonus points. Good. Right. So the 3 configurations are 1, 2, 3, depending on what terminal is the common terminal. The other one you decide based on input and output. You decide whether it's in order to make it an amplifier, right? So common emitter, common collector, and common base. Similarly for MOSFETs, so this has to be here. Base, collector, base, emitter, collector. the MOSFET, so it's easy to cover both. This is, instead of emitter, what you have is source, common source, or CS. Here, CE. This is common collector, CC. This is common drain, this one, CD. And the last one, common gate, CG. This is CB. Okay. Those are the configurations that we have. So let's look at common emitter. Configuration. So in this case, base is the input, base, collector, emitter. Emitter is the common one, base is the input, collector is the output, right? Now, sometimes, for example, in the example that we did, we had a emitter resistance. We have collected emitter resistance as a feedback resistor to improve the thermal stability of the circuit. But in that case, we put a capacitor bypassing the resistor. So therefore, again, the common, though there is a resistor there, we can consider for AC signals, the short circuited capacitor makes the emitter as the ground. So therefore, that's again the common terminal. With respect to that, we have the input as the base, the output as the emitter. Now, even when there is a small resistance to control the AC gain, we still use this terminology, because again that emitter resistance, small emitter resistance, can be considered as the emitter spread resistance, which is already inside the transistor, and later on we will learn a trick which we can use to transfer that resistance in the emitter into the base side, so that emitter becomes directly connected to the ground. We will learn that later. Okay? So therefore, this is the common emitter configuration. I will not even write that. So the features of this is for BJTs, there is a current going in. So therefore, input impedances are generally not very high, because there is a diode. What you have is a diode. So therefore, input impedances are not very high, but they are not very small either. They are in the range of like 1 kilo ohms range, right? So therefore, they are moderately high. Now it's not small, it's not 100 or 20, but it's like the same values that we typically use in our circuits, right? So that's why we call moderately high input impedance, input resistance or impedance R in, right? So typically in the range of 1 kilo ohms. That's kind of the ballpark. Output impedance. Now, when we analyze the circuits, we will see that output impedance is actually the resistance RC that we connect to the circuit, right? So if you look at an example, we'll have a look at it. So therefore, the value of the collector resistor that we put determines what the output impedance is. That value typically is in the range of 10K, in that range. So there again, it's not very high like mega ohms, not very low like 100 ohms. It's moderate, right? Moderate, really high output impedance R out in the range of 10K, 50K, that range. But the specific feature about this is very high gain, voltage gain, high voltage gain, AV. Now, as I mentioned earlier also, AV is roughly equal to whatever is the resistance in the collector branch divided by whatever the resistance in the emitter branch, including the emitter spread resistance. In case where there is no specific resistor connected to the emitter spread resistance, which is a characteristic of the transistor, becomes the denominator, right. So, therefore, this is roughly equal to RC divided by RE. If it is 0, I also have simple RE, which is the emitter spread resistance. This typically, I said these are small values. RE is in the range of maybe about 100 ohms or something, right. So, if you don't, so anyways what we put here is a small value, even in the example that we had was a small value. So, this ratio is big, like 100. 100 is a high gain. So, you 1 millivolt turns out to be 100 millivolts. So, it's a big value, right. So, and also in addition to that, input current is IB. Output current is beta times IB, IC. IC is the output current. So, therefore, again current gain is also quite high, which is equal to the beta, right, in the range of 50 to 100, right, high current gain. So, AI roughly equal to beta, which is in the range of 50 to 100, let us say 100. Now, you see you have a very large current gain and a very large voltage gain. Output power is basically output voltage times output current divided by input voltage by output current. So, what you end up having is voltage gain times current gain times input voltage times the input power. So, that is really large. You gain really large power gains here. Okay. Large power gains are achieved. Now, if I draw an example circuit, this is basically what we have been looking at actually. So, because of this property, the most commonly used BJT amplifier configuration is the common emitter amplifier, because we mostly use these things to gain power, and this has the largest power gain. So, we can look at an example. So, this is very similar to what we have already seen. RC, the amplifier, you can have a emitter resistor with a bypass capacitor and the biasing circuit, which is connected to the input using a capacitor, output also using a capacitor, right. So, input voltage, output voltage. This is the current IC. That is considered the IC. Let me mark here IC, because both these currents going into the out as well as to RC are considered as the IC. So, that is your thing, and you look at the output impedance through this R out, these two terminals, between these two terminals, that is the output impedance. Input impedance between these two terminals. This is IB, this is IC, that will define the current gain. The voltage out and voltage in will define the right? So AV RC over RE, because this is short circuited. If you have an RC, if you have, if you don't have this capacitor, then I'll have to add RE also. Okay, this is the AC gain. However, one important thing to note is that if I input a signal like this, my output would look something like this, meaning that output is inverted. Output inverted, meaning that this should be negative gain. Actually, this should be less than -1, right? If it is between -1 and 0, that's no gain. Invert and shrink, but this will be negative and larger than 1, right? This is the most common configuration. This is the most common configuration. Now, let me see. Yeah, I will do the BJTs first and then draw the FET configurations rather than having both. You know, it can be done in either way, but let me do it that way. So, the second one is common collector. Common collector configuration. Obviously, in this case, that's my in. That's my V out, right? So, base collector. So, the common terminal is that. So, let me rub this off. It's confusing. Input is the base, output is the collector, right? Certainly, we could have chosen collector as the input and input as the output as the base, then it won't be an amplifier, right? So, therefore, that's not how we choose it. Features. Now, because of this arrangement, input impedance is between base and collector, where you have a reverse biased transistor. Remember, base collector junction is reverse biased, right? So, therefore, input impedance is rather high, high input impedance. High in Rin. So, in the range of 100K, right? Again, this is not very high like 1 mega ohms, but these are BJTs. So, one issue with BJTs is that high is not that very high, right? Output impedance, when you look at the output impedance, you look at from the emitter side, right? So, from the emitter side, this output impedance looks very small, low output impedance. So, R output in the range of about 100 ohms. This is what basically you will be seeing when you connect it. Output impedance is more or less this emitter spread resistance kind of thing. And voltage gain, see that input is base, emitter is output. You know that there's a diode here which is forward biased. For DC voltages, there is a 0.7 voltage drop, but for AC voltages, there is nothing, no voltage drop, basically very small voltage drop, right. So, therefore, input is pretty much the same as the output. Input and output not much different, maybe a couple of millivolts lower, but pretty much the same. So, therefore, if at all emitter is at a lower voltage than base. So, therefore, voltage gain is low, actually equal to unity and slightly less, right. So, low or unity voltage gain AB roughly about 0.999, right. And current gain, what is the input current? IB. What is the output current? IE, which is roughly equal to IC. Again we have the same voltage current gain, much larger current gain. So, current gain is again high AI in the range of 100, like beta, right. So, large current gains. Now, if I draw an example, there is no RC here, right. The difference is that there is no RC in this circuit. So, this is my input, this is my output. Now, is it the same as that I have drawn over there? Now, the reason why it does not look the same is because we have drawn the DC circuit. If you look at it in AC circuit, you know the DC voltage sources are short circuited or replaced with their internal resistance, in which case this place is the same as that place, right. So, therefore, this is the same as ground. So, in that case my input is with respect to ground this, with output is the emitter this. Now, it is the same, is not it? So, for DC you do not see it, but for AC it is the case, okay, clear? Right. And often this is used as a voltage buffer, very much, this is a very, so otherwise you would think why would I use this? If you do not get a voltage gain, yes of course there is a current gain, why would I use it? Actually this is a very widely used circuit, voltage buffer. Why? Because you should be able to say for example in computers you have logic gates, output some value and you need to connect it to some load, but that output circuit does not have much current driving capacity. It is only a voltage. If you try to draw a current, that voltage will drop. So, therefore, in other words, internal impedance of that is very high. You will see this later in the course when you talk about digital logic, but logic gate implementations, but the issue is you can't. So, in that case what you do is you put one of these things. So, this has high input impedance, so therefore, it will not draw a current from the source, but you can provide the same voltage will not change, but now I can provide a much larger IE current. So, that is a very useful thing, most often used as a voltage buffer. Buffer. So, to drive a low impedance load with a high impedance source. All right, so those are the most widely used two types of BJT configurations, but we also have another type which is called the common base amplifier, CB. That's less common in this particular course, but will be useful in the future. So here you use the so this is the common terminal base, this is the input, in, out. Again, the choice of input and output based on the gain, right? You have to have a power gain, that's why this choice. You might think IE is slightly bigger than IC, so why not using that? You will see that voltage is much bigger in collector than just a very small millivolt range voltage in AC conditions for the emitter, right? So therefore, this is basically what you have. So the features are low input impedance in the range of 20 ohms. So very low, you can see very low input impedance because of the forward biased diode. Moderate high output impedance in the range of few mega ohms, maybe 1 mega ohm or 1 to 2 mega ohms or something like that. High voltage gain, again the same one base voltage gain is about 100, right? Not current gain, voltage gain. Current gain is nothing, right? There is no gain in current, actually a little bit small. Low, unity, current gain. Right, so that's an example if I give. So you common base and you input the signal from the emitter, take the output from the collector, but this needs to be properly biased. This is plus VCC, this is minus VEE. This needs to be connected in such a way that right. So that's your input and output. So that's an example of a common base amplifier. These are much less frequently used in your course, but they are used in RF applications. So later on you will see in the third year that depending on how you connect this, whether you have to use a high frequency or low frequency applications, this model, this other configurations, they have low, the capacitive effects is prominent. So therefore, high frequency characteristics are not good. But when you do it in this way, there are better high frequency characteristics. So, you use it for that. So, reduces effect of base collector capacitor. Now, between the base and the collector, this, it's in addition to the diode at high frequencies, the capacitance between that is considered, right. So, under this configuration, that effects are the effects of that capacitor is reduced, and therefore, the bandwidth can be increased. If a capacitor reduces the effects of base collector capacitor, reducing or increasing the bandwidth, not reducing, increasing the bandwidth, increasing the bandwidth. So, therefore, can use for high frequency applications, high frequency applications. Now, since this does not have any voltage gain, we typically use a common emitter amplifier stage after this to drive the load, right, because output impedance is pretty high here. So, therefore, it cannot drive a load. If you try to draw a current, there is a voltage drop across this 1 mega ohms large resistor. So, therefore, when you feed it, when you connect it to the load, we typically have a common emitter stage after this. Okay. Oh, I did not give you the attendance sheet, but anyways, now I do not think we will have enough time, but try to sign, but sorry about not sending, but I can put all one for everyone, but attendance, that is okay. Sign the others also, even if you can't sign, that is okay, do not worry, right. So, this can be used to drive a high so this can be used as a constant current source. Do not worry about the signature. If you can't, if it does not reach you by the end of the class, do not worry about it. I will put everybody is present. It's okay. So, you can use this as a constant current source. The use of this is you can drive a capacitor using this constant current, so that it can generate a linear ramp signal, right. I is constant, C dV over dt is the voltage. So, you can obtain by I integrated over time. So, constant integrated over time becomes a ramp, right. So, this typically uses we use for that purpose also, right. Okay, now I think I have about 15 minutes. Let us try to go through the the MOSFET amplifier configurations also very quickly, very similar to the BJT configurations, just the names are different. They have very similar characteristics also. The difference though is that because of the MOSFET's gate to body, the gate to channel oxide layer, input impedance, the current that is drawn is very small, input impedance is very large mega ohms range input impedance. So, that is a very distinct difference between BJTs and FETs, and also FETs are much faster because lower currents, they can be switched quickly. So, therefore, for fast applications, high frequency switching applications, digital circuits, we use MOSFETs, whereas to drive large currents, slow but large currents, we use BJTs. Also, when we when we design circuits using discrete components, the FETs, because of this capacitor, they are more susceptible for static discharge. The gate to channel capacitor can get damaged due to static discharge. So therefore, when we typically make discrete circuits, we use these amplifiers, right? So it's more common to design using discrete components with BJT amplifiers, whereas the ICs, when you want to design ICs, when you fabricate, it's much easier to design using the FETs. So both are used today, but MOSFETs are by far the most widely used type of transistors. So the equivalent of common emitter is the common what? Common source for the MOSFET, right? Common source or CS, right? An example, which is identical to what you had earlier for the common emitter, but yeah, identical to what you had previously, but you have, instead of a BJT, you have a FET, right? Again, you have a biasing circuit to ensure you have a signal before, even when the negative signal is applied. So the features, very high Rin. Obviously, IG is 0, right? Input gate current is 0. So therefore, this is very high input impedance in the range of ideally infinity mega ohms, in the range of mega ohms. Moderate R out in the range of 10K, which you will be again seeing that it's equal to RD, the value of RD, equal to RD. So if you choose a large RD, output impedance will be large. If you choose a small RD, output impedance will be less. But remember, the gain of the amplifier, again, RD divided by RS. Okay? So therefore, if you make RD very small, the gain will be very small. So that's a compromise, right? Voltage gain is moderate. This is roughly equal to RD over RS. Oh, this is plus 1 over GM also. This is like the emitter spread resistance what you have there. So this is, if this is 0, that is when you don't have a resistor in the emitter, this will be GM RD. But again, it's a negative quantity. Negative quantity. VDS over VGS. as a voltage gain. So this is open circuit voltage gain. Obviously, when you connect a resistor as the load, this is going to, instead of RD, you will have RD parallel the load, right? So when you connect a load parallel in the AC circuit, it's like something like this, right? In the AC circuit, because this side is short circuited to ground. Right? So even if you have a resistor here, that appears as a parallel resistor to RD. So therefore, when load is connected, AV is actually equals to roughly equal to minus GM RD parallel parallel 1 R 1 OG sorry RL. Okay. Poor high frequency performance. A poor performance at high frequency. Similar to common emitter amplifier, BJT config. Right, if you want, you can add this emitter resistor there to stabilize this, and often we do use it, but then things become a little bit more complicated, but we'll try to do an example to understand that also, right? Okay, so the next one that we have is common drain amplifier. So common drain, just like common collector, right? So this is common drain CD, like the BJT common collector, right? So so it's pretty much the same as the common common collect amplifier. So what are the features? Unity voltage gain. Unity voltage gain, the same voltage here appears here. The voltage gain AV is equal to RL over RL plus 1 over GM. So that's basically, if depending on GM, this value will vary, but definitely less than 1, right? So if GM is very large, it will be 1. If GM is small, there will be another term here which is greater than 1, so that will be less than 1. Large input impedance are in high, very high, are in, again the same as the previous one, you have the oxide layer there, so this is in the range of mega ohms. This is in the mega ohm, right? What is the output impedance? It's in parallel with RS, and also there's a GM, so the parallel connection between those two, right, will be small. So it will be moderate, R out, moderate. The last one, common gate, or CG configuration. This is similar to common base of BJT, the amplifier. So, so that's again, input is this, output is here, sorry, V out is there. Low input impedance, which is equal to 1 over GM. So that's the input impedance that you have. So between the source and the drain, source and the this is source, this is the drain, this is the gate, right? So moderate output impedance. Output impedance, when you look at it in the small signal model, this will be short circuited, so it will be basically this resistor there. So, okay, so this is RD. So in the range of maybe 10K or something. And high voltage gain, which is basically plus, this is a positive one, previous one is negative, GM times RD. You have a positive gain, GM times RD. This is the open circuit. When you load it, it becomes loaded. This becomes GM RD parallel RL. You don't have to memorize any of this, we will be deriving them, okay? Don't try to memorize this, but just to give you an idea about the values, okay? Good high frequency response, so this is better for high frequencies. Good high frequency response, and similar to common base amplifier. Right, so these are the common these are the configurations, the BJT and MOSFET configurations that we have. In general, MOSFETs have higher input impedance, much faster, but can only handle lower levels of currents. Whereas BJT circuits, much slower, but can handle much larger currents, and input impedances are much smaller. Output impedances can be moderately low, like 100 to less than 100 is possible. Okay. So when we use them, when you use VLSI designs in the chip making, MOSFETs are almost exclusively used, whereas when you try to design things using discrete components like audio amplifiers and oscillators and things like that, we use BJTs. And when we need larger currents, we use output stages of BJT stages, right? But input stages, if you want to make high input impedance stages, we use MOSFETs so that no currents are. That's why if you look at an op-amp, in an op-amp inside, these things will be used like input stages. There will be a lot of, there will be a MOSFET stage. Output will be a Darlington pair or some large current capable BJT circuit, right? So that's where we are going to stop here. Please make sure you go through the rest of the lecture notes. Now on Friday, we have a international conference going on here. So I will try to take the 11 to 12 lecture as much as possible, but if I am unable, I will inform you in advance. Okay? My plan is to come and do the 11 to 12 lecture. I'm not going to do the one and a half hours. Today I did 2, so just 1 hour I will try to cover, if possible, right? Okay, if you have any questions, you can ask, otherwise we may leave. Thank you.